In the mid-1960s, a computer was not something you carried in your pocket. It was a room-sized mainframe, often custom-built, jealously guarded in a university or military lab. Each machine spoke its own dialect, different operating systems, different data formats, different ways of talking to terminals and peripherals. If you wanted to run a program on a computer across the country, you physically mailed tapes or printouts. Inside the U.S. Department of Defense, a small group at ARPA, the Advanced Research Projects Agency, wondered if there was another way. They were funding research at places like UCLA, Stanford Research Institute, UC Santa Barbara, and the University of Utah. Each site had powerful computers, but they were islands. Larry Roberts, brought to ARPA from MIT's Lincoln Lab, was tasked with building a network to link these incompatible systems so researchers could share time and software. The challenge wasn't just incompatibility. ARPA also cared about resilience. The Cold War was underway. Planners worried that a single knocked-out switching center could cripple communications. The traditional telephone model, circuit switching, where a fixed path is reserved end-to-end, was fragile and inefficient for bursty computer traffic. In parallel, outside ARPA, people were rethinking how networks might work. At RAND, Paul Baran described a distributed communication system where messages were chopped into small blocks and sent independently through a mesh of nodes that could reroute around damage. In the UK, Donald Davies at the National Physical Laboratory independently developed a similar concept, coining the term packet. The key idea was radical for its time. Instead of setting up one dedicated path for an entire conversation, break data into packets, label them with destination information, and let intermediate machines store and forward them, choosing the best route on the fly. Some historical accounts emphasize Baran's influence on ARPA more. Others say Davis's work had more direct technical impact. But by the late 1960s, packet switching was the conceptual foundation. The missing piece was a practical device that could sit between host computers and phone lines and actually do this job in the real world. That device would be called the Interface Message Processor, the IMP. By 1968, Larry Roberts and his colleagues at ARPA had moved from concept to action. They drafted a request for proposals, an RFP, asking industry to build the packet switching nodes and the initial network connecting 4 university sites. It was an unusual government contract. ARPA wanted not just hardware, but new protocols, software, and operational procedures for something that had never existed. Big names took notice. Companies like IBM, Raytheon, and others had experience building communication systems and mainframes. On paper, they were the obvious contenders, but the RFP's technical demands were awkward for large hardware-centric firms. They called for flexible, software-driven packet switching, rapid development, and close collaboration with academic researchers. Bolt Beranek and Newman, BBN, was different. Based in Cambridge, Massachusetts, BBN was known more as an acoustics and consulting firm than as a computer manufacturer. They had worked on time-sharing systems and had a small but very capable computing group. Within BBN, engineer Frank Hart pulled together a team and crafted a proposal that treated the IMP as a specialized software-rich minicomputer, not a fixed-function box. BBN's bid emphasized reliability, modularity, and a clear plan for building, testing, and deploying the first 4 nodes in less than a year. They proposed using off-the-shelf minicomputers, heavily ruggedized, with carefully designed interfaces to host machines and phone lines. Their document laid out how routing, congestion control, and error handling might work, at least at a high level, on day 1. Some accounts suggest that larger vendors submitted more conservative proposals tied to existing circuit switching ideas, or were simply less willing to accept ARPA's tight schedule and open-ended research flavor. Whatever the exact reasoning inside ARPA's selection committee, in early 1969, the dark horse candidate won. BBN got the contract to build the ARPANET's interface message processors and operate the fledgling network. Once BBN had the contract, they faced a very concrete question. What machine should actually run the IMP software? They weren't going to design a CPU from scratch. The schedule was too tight. Instead, they evaluated existing minicomputers that could be bought, modified, and shipped to sites. The IMP needed to be small enough to fit in crowded machine rooms, but powerful enough to handle multiple 50 kilobit per second phone lines and several host interfaces. It had to run continuously, recover cleanly from crashes, and survive shipping, power glitches, and the occasional bumped cabinet. Memory was a severe constraint by modern standards. They were thinking in terms of tens of kilobytes, not gigabytes. BBN looked at several candidates. There is some disagreement in recollections over the full list, but systems from DEC and Honeywell were seriously considered. They needed features like interrupt handling for multiple communication channels, fast context switching, and hardware support that could be adapted for direct memory access to move packets without wasting CPU cycles. They ultimately selected the Honeywell DDP 516, a 16-bit minicomputer that could be ruggedized for military environments. BBN worked with Honeywell to produce a variant with core memory, no moving part storage, and front panel access suitable for diagnostics. The choice was pragmatic. The 516 wasn't glamorous, but it was reliable, reasonably fast for the time, and crucially, available in the quantities and timeframe ARPA required. Each IMP would be built around this Honeywell minicomputer with custom interface hardware designed by BBN engineers to connect to both the host computers, large mainframes like the SDS Sigma 7 at UCLA, and to leased long-distance phone lines. The result would be a refrigerator-sized box that could quietly sit beside a university's mainframe and take on the messy work of networking. With hardware chosen, BBN's team had to invent what it meant for a general-purpose minicomputer to act as a packet switch. Frank Hart led the project, with key contributions from engineers like Severo Ornstein, Will Crowther, and a young Bob Kahn, among others. Their tasks spanned hardware interfaces, real-time software, and network algorithms. Inside each IMP, packets would arrive from either a host computer or a neighboring IMP over a leased line. The IMP had to buffer them in memory, check them for errors, decide where to send them next, and then transmit them onward, all while juggling many packets at once from multiple directions. This is the store and forward model in action. The IMP software was written in low-level code, tuned to fit in limited core memory. It implemented a routing algorithm that maintained a table of known neighboring IMPs and link costs. When a packet arrived, the software looked up the best outgoing line based on that table. Routing updates themselves were sent as packets, allowing the network to adapt if a line went down or became congested. Error detection was also crucial. The team used checksums to detect corrupted packets, discarding bad ones and relying on higher-level protocols or the endpoints to retransmit. They implemented mechanisms to prevent a single misbehaving host from flooding the network, and they designed timeouts and acknowledgements so that an IMP could tell whether a neighbor was alive and responding. In effect, BBN turned the Honeywell 516 into a dedicated network appliance whose only job was to move packets reliably between hosts and lines. Later terminology would call this device a router, but at the time, it was simply the interface message processor, the heart of each ARPANET node. Recollections sometimes differ on who implemented which specific feature, but the overall architecture, store and forward packets, dynamic routing, and robust error handling became the template for future internet routers. All of this logic inside the IMPs would have been meaningless without a physical network to connect them. In 1969, that meant leased phone lines from the existing telecommunications carriers, primarily AT&T and its regional operating companies. The initial ARPANET design called for 50 kilobit per second lines, fast for the time, and significantly above typical dial-up speeds. The first 4 sites selected were UCLA, the Stanford Research Institute in Menlo Park, UC Santa Barbara, and the University of Utah in Salt Lake City. Each location would receive an IMP and a high-speed line linking it to at least one other node, forming a small but non-trivial mesh. For example, a line would run between UCLA and SRI, another between SRI and UCSB, and so on, creating redundant paths. Coordinating this was messy. BBN's engineers had to work with phone company technicians who were used to circuit-switched voice service, not experimental data networks. There were issues of line conditioning, noise, and timing. Modems, or more precisely datasets, had to be configured correctly at both ends. Installers sometimes showed up without a clear understanding of what this computer network was supposed to do. The IMP hardware itself had to interface cleanly with these lines. BBN designed communication controllers that could synchronize to the bitstream, handle framing, and present clean packets to the IMP's CPU. They also had to engineer robust logging and diagnostics so that when a line went down, they could tell whether the problem was in the IMP, the modem, or hundreds of kilometers of copper. By late 1969, the leased lines between the first nodes were in place. or close to it. The picture that emerged was still small, but it was recognizably a wide-area packet network, a handful of specialized computers linked by dedicated high-speed data circuits, ready for the first real traffic. The moment when theory met reality came in the fall of 1969. The first IMP was delivered to UCLA on September 1st, installed in a room in Boulter Hall. Graduate student Steve Crocker and his colleagues, working with BBN engineers, wired it to their Sigma 7 host. Over the next weeks, more IMPs were installed, at SRI, at UC Santa Barbara, and at the University of Utah. On October 29, 1969, a famous test took place between UCLA and SRI. Programmer Charlie Klein at UCLA attempted to log in remotely to an SDS 940 host at SRI using the ARPANET connection. The plan was simple. Type login on a terminal at UCLA, have the characters travel as data over the phone line through the IMPs, and reach the host at SRI. As Klein typed, UCLA's host sent characters to its IMP, which packaged them into packets and forwarded them over the 50 kilobits per second line to SRI's IMP, which then handed them to the SRI host. According to widely told accounts, the system crashed after the second character. The SRI machine went down after receiving L and O, so the first message on the network, at least in popular memory, was just "OO." Later that night, after fixing the problem, they tried again and successfully completed the login. From that point on, data was flowing across a packet-switched network between two distant sites. Some historians caution that the exact sequence of events is remembered slightly differently by participants, and that it's hard to say with certainty what the very first full successful application-level message was. But there is broad agreement that by the end of 1969, the 4-node ARPANET was operational, and the IMPs were doing their job. This modest first connection didn't look like today's internet, but it demonstrated a working prototype of the key idea. Independent computers, separated by long distances, communicating through a mesh of packet-switching nodes. From the beginning, the IMPs were only one layer of the story. To make the network actually useful to programmers and researchers, there had to be a common language, protocols, above the raw packet forwarding. ARPA encouraged the creation of the Network Working Group, led informally by people like Steve Crocker, to define how hosts would talk over the IMPs. At the lowest level between IMPs, BBN designed an IMP2 IMP protocol that handled things like sequence numbers, acknowledgements, and routing updates. This protocol made sure that packets sent from one IMP to another arrived in order, without duplication, and with reasonable reliability, or that failures were clearly signaled. Above that sat the Network Control Protocol, NCP, which defined how host computers established connections, flowed data, and multiplexed multiple logical conversations over a single physical link to their local IMP. NCP ran in the host operating systems, not in the IMPs. It treated the IMP network as a reliable pipe and provided services to applications like remote login and file transfer. Over the 1970s, as ARPANET grew and other experimental networks appeared, these protocol layers evolved. Work led by Vint Cerf and Bob Kahn produced a new suite, TCP/IP, designed not just for one network like ARPANET, but for interconnecting many different kinds of packet networks. In the late 1970s and early 1980s, TCP/IP was refined and adopted, culminating in the famous Flag Day in January 1983, when ARPANET hosts switched from NCP to TCP/IP. During this transition, the IMPs adapted. Their core job, forwarding packets and maintaining routes, remained, but they were updated to understand and carry IP datagrams. Exact details of how each IMP software evolved are not always documented in public sources, but the general picture is clear. The IMP's packet switching layer became the substrate over which the modern Internet protocols ran. By the late 1970s and early 1980s, the original IMPs were aging. BBN and others developed successors, smaller, faster packet switches, and eventually purpose-built routers that could handle higher speeds and more complex routing. Commercial vendors entered the space, building on concepts that the IMP had proven in practice. Yet the basic architectural role of the IMP did not disappear. Modern routers, whether in a home network or at the core of the Internet, still perform store and forward, or closely related behaviors, maintain routing tables, and implement protocols to discover and adapt to network topology. They are descendants of the IMP in function, if not in brand. BBN continued to play a role in networking history, operating parts of ARPANET, contributing to protocol development, and later participating in commercial internet infrastructure. Over time, however, the specific term IMP faded from everyday use, replaced by packet switch, gateway, and eventually router. As with many foundational technologies, there have been debates over credit, how much to attribute to BBN versus ARPA program managers versus academic researchers, and how to weigh earlier theoretical work by Baran, Davies, and others. The historical record shows a genuinely collaborative, sometimes messy process, with ideas flowing among many institutions. What is not in serious dispute is that the interface message processor made ARPANET real. It solved the concrete engineering problem of interconnecting incompatible host computers over long-distance lines using packet switching, and it did so in a way that could scale and evolve. That refrigerator-sized Honeywell-based box, humming away in a university machine room, is one of the quiet ancestors of every router that now directs traffic across the global internet.